Today we will learn the fundamental anatomy of a relational database. Relational databases consist of tables. Let's say we have a relational database for a local football team. Within our team database, we will place database tables providing data about our team. We might have a player table storing the players on the team. We also might have an order table showing all of the food orders that the players make at the team cafeteria. Now, let's look at the anatomy of a database table. We will call the table player, since each entry in the table will be a player on the team. The first row of the table is a row of column headers called attributes. These attributes describe what data we are storing about the player in its corresponding column. For the player identification number attribute, we are storing the identification number of each player in its corresponding column. For the name attribute, we store names. And for the age attribute, we store ages. Each row will represent a player. For the first player, let's give her an identification number of 1, the name, Kate, and the age of 26. For the second player, let's give him an identification number of 2, the name, Rob, and the age of 29. Each row in a table is called a tuple. Think of a tuple as an ordered list of values, where each value corresponds to a specific attribute. In database theory, a table is referred to as a relation because it represents a relationship between various attributes or columns. This relationship is defined by the connections between the data values within each row, or tuple. In the context of the player table, we establish a relationship between the attributes that uniquely identify a player, namely, identification number, name, and age. Each row that populates these attributes with specific data values forms a cohesive relationship where the collective data describes a distinct individual player. For a moment, let's look specifically at the age attribute. The attribute currently contains values 26 and 29. To accurately represent age in years, the attribute should accept whole numbers, including 0 and positive integers. Negative integers are not applicable. The set of allowed values for an attribute is referred to as its domain. The domain can be customized as needed. For example, you could set the domain of the age attribute to any decimal number that is greater than or equal to 0. In this case, we can add decimal points to our ages if we'd like. Domains must be atomic. This means they should contain only indivisible, single units of data. Consider a table that stores friendships between players. In this table, each player is associated with a unique player identification, which is listed in the player ID column. To store their friends, we might initially think to list all friends in a single friend identification column. For the first row, this means that the player with an identification number of 1 is friends with the players with the identification number values of 2 and 3. This may seem like a good approach. However, this approach violates the atomic domain requirement. Instead, we should design the table so that each row represents a single friendship, pairing one player with one friend. This ensures the friend identification attribute's domain consists of individual, indivisible values meeting the atomicity requirement. Sometimes, a value may either be unavailable or even unapplicable. For example, we might be storing an email, but the person doesn't have an email or didn't share it with us. In this case, we fill in the value with a special value called null. Finally, let's understand a schema. A schema is a blueprint or detailed plan that outlines the structure of something. For example, the structure of the player relation is defined by its relation schema. Think of a relation schema as a template. This template specifies the attributes or characteristics of the relation. We write this template as player, open parenthesis, attribute 1, comma, attribute 2, comma, and so on, close parenthesis. We now have the table name, followed by a list of its attributes, which is the relation schema of the player table. The actual implementation of this blueprint is called the relation instance. This instance changes regularly as the player data is modified, but the relational schema changes much less often, if at all. For the overall database, the design of the database is called the database schema, while the actual database and its data is called the database instance. In part 2, we'll understand relational databases even more.